When charges are arranged in a line or a plate of some kind, an interesting phenomenon happens with the electric field. The field lines that we get will be perpendicular to the plate, and they'll be very parallel. At the corners, they can start to deviate a little. And by symmetry, we'll get the same kind of situation on the bottom side here. Similar to a point charge, just stretched out. At the ends, of course, we could get something like this. There we go. Now let's try field lines for a positive plate near a negative plate. By plate, we mean that in 3 dimensions, it would be flat, like a piece of paper with some thickness. And one of them is charged positively. And another plate here that's parallel to it is charged negatively. What will the field lines be between them? Well, you could imagine a positive test charge. And what would it want to do if it was located between those two plates? Well, remember, positives are repelled by other positives and attracted to negatives. Now we're going to imagine there's no gravity in this situation. If that were the case, then the positive charge would certainly be attracted to the negative plate. And that's what our field line will show. The field line shows the direction that positive charges would want to go. At the corners, we start to get a little bit of bowing of the lines. But between the two plates, it's actually very, very uniform. And this turns out to be very useful in electronics. It'll be a device called a capacitor that we look at in the future. Now, outside the parallel plates, we actually don't see a lot of field out there. It's very weak. The reason being that if you're a positive test charge out here, you are repelled by the positive plate, but you're also attracted to the negative plate. Now, the positive plate is closer to you, so you'll be slightly repelled more than attracted. And the same kind of phenomenon would happen here. You'd be a little bit more attracted to the negative plate than you would be repelled by that positive plate. But the field is very weak out there. We could draw maybe just a couple lines. There we go. Now let's try an application of a charge in a parallel plate capacitor. It says a region in space has a uniform electric field strength equal to 400 newtons per coulomb. So let's write that down. E is 400 newtons per coulomb. The field points to the right. And we're going to have a 2 microcoulomb test charge with a mass of 0.1 grams inside the uniform field. So let's write those things down. We've got Q, 2 microcoulombs, M, 0.1 grams. Assume no gravity. Can we draw the charges that each of the plates has on it to cause this uniform field? Well, we see that the field lines are pointing to the right. Field lines always point toward negatives and away from positives. So this must be a negatively charged plate, and this would be a positively charged one. How could you do this? Well, just imagine taking a piece of aluminum foil, for example. That's a thin sheet. So if you could just put electrons on one of the aluminum foil pieces and take electrons away from the other aluminum foil piece, then you could create two parallel pieces that would make this field arrangement. Can we describe the motion of the charge in the field after it's released from rest? Because this is a charged particle, it will respond to the external field that it's in. So what will happen is it'll accelerate. Which way will it accelerate? Well, positives are attracted to negatives. So it'll accelerate to the right. It'll follow the field lines, and that's what positive test charges do. They are pushed in the direction of the field. What is the magnitude and direction of the electric force on this charge? For that, we're going to use the formula Fe equals QE. Okay, so we've got 2 microcoulombs times our 400 newtons per coulomb, 0.0008 newtons directed to the right. What would be the acceleration of the charge as it moves in the field? All right, so for that, we're going to need Newton's second law. Here, the net force is the electric force. I'm going to change the grams to kilograms. (8 meters per second squared). After the charge has moved 1 meter, how fast will it be moving? Well, for this, we'd want to think about the different motion formulas that are available. This one would work very well. We're going to start off with 0 speed. Have a displacement of 1 meter. Final speed, 4 meters per second. How long does it take the charge to move 1 meter in the field? This formula will work well for that. .5 seconds.